Usually when we look at a complex system, there's this underlying expectation of precision, like with engineering or modern medicine, right?
Right. Yeah, absolutely.
Like if you fall and break your arm, you go to the hospital, they take an X-ray, and it just shows that stark, jagged white line right there on the black background. And the doctor just points to it and says, there it is. That's the problem.
Exactly. It's totally binary. It's either broken or it's not broken. You can literally see the structural failure right in front of you.
Yeah, and it's clean. And in a weird way, I feel like even when it's bad news, that clarity is deeply comforting.
Yeah.
Because we as humans, we just desperately like things to be visible, right?
Yeah, for sure.
To be neatly categorized, to have a very definitive starting point and ending point.
But then, you step out of the hospital and into the world of planetary mechanics, and you start looking at global climate systems or atmospheric chemistry and interlocking ecosystems, and suddenly that pristine X-ray machine is just completely broken. We're looking at a diagnostic landscape that is, well, honestly, it's incredibly murky.
It is the absolute definition of diagnostic muddy waters. And that is exactly what we're diving in today. So welcome to a brand new deep dive. We know you're here because you want to be well-informed, right? You've got a busy life. You do not want to feel just completely overwhelmed by the absolute barrage of data out there, but you still want the real story.
Right. The actual context.
Exactly. And today's stack of sources is massive. I mean, we are looking at a comprehensive, really incredibly relevant news-style report on the 2026 climate crisis.
And our mission today is really to act as your guides through this vast, sometimes totally contradictory amount of information.
Yeah.
We're going to unpack the extreme summer of 2026. So we're starting with Europe's what they're calling virtually impossible heat waves and the official arrival of a very strong El Niño.
Which is huge.
It is. But we aren't just stopping at the surface weather reports. We're going down into the fundamental physics, specifically Earth's doubling energy imbalance. We'll look at the vanishing snow reserves of Swiss glaciers, the rapid rewiring of global ecosystems, and critically, the human response to all of this.
Right, because humanity isn't just sitting on its hands here.
Exactly. We have groundbreaking genetic technologies like CRISPR actively being deployed to secure our food supply, alongside this really massive push for inclusive climate action.
Okay, so let's unpack this. It is a mountain of data, I know, but we're going to break it down for you. We've got some pretty serious scientific analysis to get through, but we're going to keep it approachable. Because before we can talk about the extreme heat sitting outside our front doors right now, we really need to understand the invisible physics driving it, right?
Yeah, you have to look at the engine.
Exactly. So let's start with the macro picture, the fundamental planetary engine.
That is the perfect place to start. Because the weather you experience, the rainstorm, the heat wave, the drought, it's just a symptom of that much larger planetary engine. And right now, the most crucial metric of that engine is something called Earth's energy imbalance.
Right.
And according to the recent climate indicators in our sources, this imbalance has actually doubled in recent decades.
Now, when I was reading through the stack, this term just kept popping up, energy imbalance. But the way I understand it, it's essentially a planetary ledger, right? Like a thermodynamic accounting system.
That's a great way to put it.
Because every single day, the Earth receives this massive, incomprehensible amount of energy from the sun in the form of shortwave radiation.
Yeah.
Sunlight.
Right.
And if the Earth is going to stay at a stable, livable temperature, it has to radiate that exact same amount of energy back out into deep space in the form of long-wave infrared radiation, basically heat.
Precisely. It's an energy budget. Energy in literally must equal energy out.
But because we've been thickening the atmosphere with greenhouse gases, carbon dioxide, methane, nitrous oxide.
The big ones, yeah.
Right. Those gases act like a molecular blanket. So they are transparent to the incoming sunlight, but they're completely opaque to the outgoing heat.
Exactly.
So they trap some of that infrared radiation, meaning the energy coming in is now greater than the energy escaping. And that difference, that leftover surplus of heat, that is the energy imbalance.
That is exactly the mechanism.
Yeah.
And it's measured in watts per square meter. But what the researchers are highlighting here is that the rate at which we are trapping this excess energy has completely doubled.
Wow.
Yeah, we are accumulating heat at a record pace. And it's pushing global warming to hit 1.37 degrees Celsius by 2025. And here's why that thermodynamic ledger matters so much. A doubled energy imbalance basically acts as a loaded spring for the entire climate system.
Because that heat has to go somewhere, right?
Yeah.
It's like wearing a really thick, heavy winter parka while you're running on a treadmill.
Oh, that's a good analogy.
You're generating all this heat, but the coat is trapping it right against your body. The heat has nowhere to go but inward, into your tissue, physically raising your core temperature.
Yeah, the heat is baked into the system. Even if we stopped all greenhouse gas emissions, like this very afternoon, that surplus energy is already inside the Earth system. It's waiting to manifest.
It's locked in.
Right. It will eventually express itself as stronger hurricanes or melting ice sheets or, prolonged heat waves.
But the climate is never just one variable, which is what makes it so fascinating and honestly so frustrating to read about. Because this surplus heat is constantly interacting with other things we put in the sky.
Yeah.
And this brings up a study from the Hebrew University of Jerusalem that honestly blew my mind.
The aerosol study.
Yeah, it's about aerosols.
Yeah.
Because I always operate under the assumption that pollution just directly equals warming. But this research points out that aerosol cloud interactions are doing something completely paradoxical.
Yeah, what's fascinating here is that aerosols are essentially the ultimate wild card in climate modeling. And when we say aerosols, just to be clear, we aren't talking about hairspray cans.
Right.
We're talking about microscopic particulate matter suspended in the atmosphere. So this is the sulfur dioxide from burning coal, the soot from diesel engines, dust kicked up from agriculture, and black carbon from wildfires.
Basically the stuff that makes the sky look super hazy and gives you asthma.
Exactly. But in the atmosphere, these tiny particles act as what we call cloud condensation nuclei. Because water vapor in the air, it needs something physical to cling to in order to actually form a droplet.
Oh, interesting.
Yeah. So when you have a lot of aerosol pollution in the sky, you are basically providing trillions of tiny little seeds for water vapor to condense around.
So more pollution means more clouds.
Well, it means different clouds. This is known as the Toomey effect. So if you have a really clean atmosphere with very few particles, the water vapor condenses into fewer, larger droplets. But if you have a highly polluted atmosphere with tons of aerosols, the water condenses into many, many incredibly tiny droplets, and clouds that are made of tiny, densely packed droplets are physically brighter. They're whiter.
Wait, really?
Yeah, so they act like a giant mirror. They reflect incoming sunlight back into space before it can even reach the surface and get trapped by our greenhouse gases.
Wow. So human pollution is literally acting as a reflective shield, like it's masking the warming.
Yes.
Yeah.
Paradoxically, our dirty air has been shielding us from the full force of our own greenhouse gases. It's a cooling effect. But, and this is the kicker, the new research from Hebrew University shows that the timing and the evolution of these clouds matter immensely, and it is highly, highly complex.
How so?
Well, in the short term, they cool the environment by reflecting light, like we said. But over longer time scales, depending on their altitude or how they mix with other gases and how they alter the lifespan of the cloud itself, they can actually start absorbing heat. Or they can totally disrupt regional rainfall patterns.
That is a terrifying paradox.
Yeah.
Because if we magically cleaned up all the smog and particulate pollution tomorrow, which, we absolutely need to do because millions of people literally die from poor air quality.
Right, it's a huge public health crisis.
Yeah. But if we did that, we might actually trigger a sudden, brutal spike in global temperatures just because we wiped away the mirror.
Exactly. And this raises a really important question for climate modelers, and it helps explain the lingering uncertainty in future temperature projections. To know exactly how hot 2050 will be, we don't just need to know how much carbon we'll emit.
Right.
We actually have to accurately predict exactly how fast we're going to clean up our localized air pollution and exactly how those specific cloud formations will react to the cleaner air.
That sounds impossibly complicated. And just to add another layer of absolute chaos to the atmospheric modeling, there's a dispatch in our sources from the University of New Hampshire looking at space weather.
Oh yeah, this is wild.
Right. They found evidence that solar outbursts, like literal flares from the sun hurling charged particles at Earth, can temporarily interact with the atmosphere in ways that subtly weaken rain and snow events across North America.
It's just a brilliant reminder that Earth doesn't exist in a vacuum. The sun isn't just a static, glowing light bulb. It is a violently active star.
Yeah.
And when those charged particles hit our magnetic field and cascade into the atmosphere, they can actually alter the electrical charge of air masses, which subtly influences atmospheric pressure and cloud formation. It's a tiny driver compared to the massive hammer of greenhouse gases. But if you want precision in your models, you apparently have to factor in the mood of the sun on any given Tuesday.
Okay, so the sky is incredibly complicated. We have trapped heat, we have pollution acting as this chaotic mirror, and we have solar flares altering precipitation. But let's follow the physics here. The atmosphere can only hold so much heat, right?
Right.
So that massive surplus of energy from the energy imbalance has to physically go somewhere.
And over 90% of it goes straight down to the great absorber, the ocean.
90%.
Yes. The heat capacity of water is just staggering. If the oceans hadn't been absorbing this surplus energy over the last century, our surface atmospheric temperatures would be completely unlivable. We would have literally cooked ourselves decades ago.
But the ocean isn't just this uniform bathtub of water that warms evenly, is it?
Mm.
Because our sources highlight a fascinating analysis from Florida State University that looked at the deep differences in how the Atlantic and the Pacific Oceans are reacting to this heat.
Yeah, this is a really crucial distinction. The researchers found that these two massive bodies of water are basically following very different rules.
Okay, how so?
Well, in the Atlantic, the long-term temperature changes are much more closely tied to direct human-caused emissions. The warming trend there is a very clear, persistent signal of our greenhouse gases at work.
And the Pacific.
The Pacific is so unthinkably vast that its changes appear more strongly shaped by natural, slow-moving internal variability. It has these massive, multi-decadal cycles, like the Pacific Decadal Oscillation, or PDO.
I'm going to make sure I understand the mechanics of that. The PDO is basically a massive reshuffling of where the warm and cold water sits in the Pacific Basin, right?
Yeah.
And it operates on a cycle of like 20 to 30 years.
Exactly. During a cool phase of the PDO, massive amounts of cold water upwell from the deep ocean along the coast of the Americas, and essentially swallows heat and keeps the global surface temperature slightly depressed.
Oh, wow.
Yeah, it can literally mask the human-caused warming signal for decades, but when it flips to a warm phase, all that heat is unleashed back toward the surface. So the Florida State research really underscores that while the Atlantic is a clear thermometer for global warming, the Pacific's internal sloshing can basically hide or amplify the danger for decades at a time.
And speaking of hiding heat, we have to talk about what is happening in the deep ocean, specifically the Southern Ocean around Antarctica. We have new satellite data in here revealing vertical currents that are diving 3,000 feet below the surface. 3,000 feet.
It's massive. And if we connect this to the bigger picture, this is really Earth's life support system in action. This is called deep water formation.
Okay.
The Southern Ocean acts like a giant icy lung. The water on the surface there gets incredibly cold, and because it forms sea ice, the water that's left behind becomes highly saline, very salty.
In cold, salty water is denser and heavier than warm water, so it sinks.
It sinks like a stone, it plummets 3,000 feet into the abyss, and as it goes down, it acts like a massive plunger. It physically drags atmospheric carbon dioxide, surface heat, and dissolved oxygen way down into the deep ocean.
So it's burying it.
Exactly. It locks that heat and carbon away from the atmosphere for centuries, while simultaneously driving the global conveyor belt of ocean currents.
But here is the terrifying part that was highlighted in our sources. Just as we are realizing how much heat is being jammed into these deep ocean currents, the very network watching the world's oceans is under immense pressure. There's a report in here that scientists are actually losing critical climate records because a major ocean observatory is set for removal.
Yeah, it's a huge logistical and financial tragedy. We rely on networks of autonomous floats like the Argo Array and fixed deep-sea observatories to measure the temperature, the salinity, the chemistry of the ocean at these extreme depths.
And I imagine it takes a long time to get good data on that.
Decades. It takes decades to build a reliable baseline of data.
It's like we finally built the X-ray machine to see the internal organs of the planet, and now, just due to funding cuts or logistical hurdles, we're just unplugging it. I mean, how can we possibly model the climate of the 2030s if we sever the timeline of data from the very engine driving it?
We can't. You just can't. If you lose the continuous data stream, you introduce massive blind spots into every single supercomputer model on Earth.
Okay, so let's summarize this macro picture before we look at the actual consequences. The Earth's energy ledger is massively unbalanced. The oceans are frantically swallowing 90% of that heat, dragging it thousands of feet deep. Meanwhile, particulate pollution in the sky is acting as this chaotic, unpredictable cooling shield.
Right.
But the oceans can only absorb so much, so fast. The heat they cannot swallow remains in the atmosphere. And in the summer of 2026, we are seeing exactly what that looks like on the ground. So let's pivot to the immediate inferno in Europe.
The sheer scale of what has unfolded in Europe is staggering. The data we're looking at describes a massive, persistent heat dome that has settled over the continent, heavily scorching the UK, France, and Spain.
Yeah.
Over 100 million Europeans are facing temperatures consistently over 35 degrees Celsius, which is roughly 95 degrees Fahrenheit.
Which, might not sound apocalyptic to someone living in Arizona or Dubai, but context is everything here.
Right.
We are talking about regions where the architecture, the urban planning, and the power grids were historically built to retain heat, not shed it. I mean, London and Paris were built for chilly, damp winters.
Right. A 95-degree day in an unair-conditioned brick flat in London with zero nighttime cooling, that is a severe medical emergency. And the infrastructure simply buckles. The reports noted a major power outage in France directly linked to the heat.
Because everyone turns on whatever cooling devices they have at the exact same time, which just spikes demand. But the heat also attacks the supply side of the power grid, doesn't it?
It absolutely does. The physical efficiency of high-voltage power lines literally drops as the ambient air temperature rises. They expand and they sag.
Wow.
And furthermore, nuclear power plants, which provide a massive chunk of France's electricity, they rely on river water to cool their reactors. If the river water gets too warm from the heat dome, they legally have to power down the reactors to avoid basically boiling the local river ecosystem.
Right.
Yeah, so you have skyrocketing demand colliding with a physically compromised supply. It is a cascading systemic failure.
But what really grabbed my attention in this stack of sources was the rapid attribution research. Scientists analyzed this late June heat wave, and they explicitly stated that it would have been, quote, virtually impossible without human-caused climate change.
Yeah, and virtually impossible is a phrase that atmospheric physicists do not throw around lightly.
Right. So how do they actually prove that? Because, climate skeptics will always say, well, it's summer, heat waves happen naturally. How does rapid attribution science actually work to say, no, this specific event is our fault?
It relies on immense computing power and Monte Carlo simulations. So scientists take a highly advanced model of the Earth's climate and they run two different scenarios thousands of times.
Okay.
The first scenario is the Earth as it exists today. So with all our historical carbon emissions, the current energy imbalance, and the current ocean temperatures, they look to see how often a heat dome of this magnitude occurs in that simulation.
And the second scenario?
The second scenario is the counterfactual Earth. They completely remove all the human-emitted greenhouse gases from the model. They reset the atmosphere to pre-industrial 1850 levels, and they run the simulation again thousands of times to see if natural variables like the sun, volcanoes, normal ocean cycles could spontaneously produce the 2026 European heat wave.
And the answer was no.
Right. It simply doesn't happen in a world without human pollution.
I think of it like an athlete who gets caught taking performance-enhancing drugs. A baseball player might hit a home run completely naturally once in a while. But when they suddenly gain 40 pounds of muscle and start hitting 80 home runs a season, smashing records every single week, you can automatically look at that and say, sure, a home run is a natural event in baseball, but this specific string of smashed records is purely chemical.
That is a phenomenal way to frame it.
This European heat wave is a chemical home run.
Yeah, the baseline has been chemically altered, and this raises a profound question that the journal Nature directly posed in their reporting. Is this simply the new climate for cities like London, Paris, and Berlin?
Which is a terrifying thought.
Because if an event that used to be a once-in-a-thousand-years anomaly is now occurring every 4 or 5 years, you have to fundamentally reclassify the geography. You no longer live in a temperate climate with occasional heat waves. You live in a subtropical climate that occasionally cools down.
And the World Meteorological Organization was very clear that this is producing major, widespread health impacts. And if we zoom out over the last half-century, the global reality of this shifting baseline is incredibly sobering. The sources detailed a massive 50-year global study showing that dangerous heat stress exposure has climbed from 16% to 22% worldwide.
And we really must recognize the dual drivers behind that statistic. The absolute temperature of the atmosphere is rising, yes, but it is also driven by human geography.
Like population growth.
Population growth and urbanization, exactly. We are building massive concrete and asphalt cities, creating urban heat islands that just trap solar radiation.
Yeah.
And we're putting millions more vulnerable people inside them just as the ambient temperature skyrockets.
Yeah. Which brings up a localized nightmare scenario that I found deeply unsettling in the research.
Yeah.
We tend to have this very sanitized idea of extreme heat, right?
Yeah.
That it just makes you sweat or gives you heat stroke if you aren't careful.
Yeah.
But extreme heat creates extreme fire. And fire creates completely new toxic environments. Duke University did some research on the soil and ash from homes that burned in the Los Angeles wildfires, specifically the Eaton and Palisades fires.
Yeah, the findings there are a stark, really frightening reminder of the urban micro impacts of climate change. Because when a natural forest burns, you're left with wood ash and carbon. It's part of the natural cycle.
Right.
But when an urban interface burns, like when a suburban neighborhood, garages, cars, and industrial parks catch fire, you are literally incinerating modern chemistry.
Right. I'd imagine if a neighborhood burns, you're incinerating 1970s lead paint, treated lumber, plastic PVC pipes.
Exactly. The Duke researchers analyzed the soil in the aftermath of these fires and found highly uneven, incredibly dangerous contamination of heavy metals, specifically lead and arsenic.
Wow.
The extreme heat of the wildfire actually vaporizes the lead paint on older homes or the arsenic used to pressure treat wooden decks. Those heavy metals go airborne in the smoke, and then they settle into the ash and soil.
And the study noted how shockingly uneven the contamination was. Like, you could have 1 square yard of soil that is perfectly safe, and literally 3 feet away, a lethal concentration of heavy metals.
Because of the chaotic aerodynamics of a fire and the specific materials that burn in that exact spot. A shed full of old paint cans burns very differently than a plastic composite deck. The heat creates the wildfires, but the wildfires chemically transform the very ground into a localized toxic hazard zone. And because the deposition is so uneven, you can't just broadly test one spot in a neighborhood and declare the whole block safe for rebuilding or safe for children to play in the dirt. It requires exhaustive, granular testing.
Wow. We literally weaponize our own building materials when the climate pushes the temperature past the ignition point. And speaking of air quality and profound landscape changes, there's also a report in here about Southeast Asia. Massive shifts in land use and deforestation are fueling a deadly air crisis there that is costing billions in healthcare and lost productivity.
It's all connected.
It just underscores that changing our environment has immediate, physical, deeply expensive health consequences. But while all of this is happening on land, while Europe bakes under a dome and California deals with toxic ash tower, there is a massive planetary-scale shift occurring in the waters of the Pacific Ocean, a shift that will dictate global weather for the next year.
We are talking about the official confirmed arrival of El Niño. According to the sources, NASA's satellite observations of sea surface height patterns have confirmed that strong El Niño conditions are currently developing in the tropical Pacific.
Okay, let's look at the mechanics of this because I want to make sure I understand the satellite tech here. The report specifically mentioned NASA looking at sea surface height. So if they are looking at the physical height of the ocean to track an El Niño, that must mean they're tracking thermal expansion, right? Like hotter water literally swells.
That is exactly the physics at play. Water molecules, when they're heated, become more energetic and move further apart. The water physically takes up more volume.
Fascinating.
Yeah, and NASA uses incredibly precise radar altimeters on satellites, like the Sentinel-6, to bounce microwave pulses off the surface of the ocean. When they analyze that data, they can actually see a massive physical bulge in the ocean, a region where the water is slightly elevated compared to the surrounding sea.
And that bulge is the vast pool of anomalous heat that defines El Niño.
Yes. Under normal neutral conditions, the trade winds blow really strongly from east to west across the Pacific, pushing the warm surface water toward Indonesia and Australia.
Right.
But during an El Niño, those trade winds weaken or sometimes even reverse. And without the wind holding it back, that massive elevated pool of warm water just sloshes back east toward the coast of South America.
And when a pool of heat the size of a continent moves across the ocean, it essentially rearranges the furniture of the global atmosphere, right?
It drastically alters the path of the jet streams. The heat transfers massive amounts of moisture and energy into the air, which shifts global rainfall patterns.
What does that look like on the ground?
Historically, this means you get intense, crushing droughts in Australia and parts of Southeast Asia, while the southern United States and the western coast of South America might get hammered with torrential rains and flooding.
Wow.
It also tends to bump up the average global surface temperature significantly because so much ocean heat is suddenly venting into the air.
So we have a strong El Niño arriving on top of a baseline where the Earth's energy imbalance is already doubled, which brings up a fascinating methodological shift I saw in the sources. Scientists are now rolling out something called the New Relative Niño Index. Why do they need a new index? Was the traditional way of measuring El Niño no longer working?
Well, the old index wasn't mathematically broken, but the ocean it was trying to measure has just changed too much. The traditional index simply measured the absolute temperature of that specific patch of water in the equatorial Pacific. If it got above a certain temperature threshold, boom, you have an El Nino.
But because global warming has raised the baseline temperature of the entire global ocean so drastically, that traditional metric is getting distorted.
Exactly. If the whole ocean is hotter everywhere all the time, hitting that traditional temperature threshold doesn't mean as much. You need a relative index to measure the difference, the gradient between the El Nino region and the rest of the tropical ocean, in order to truly gauge how much anomalous energy is actually going to be injected into the atmosphere.
Wait, let me push back on this a little bit. If the whole ocean is hotter, doesn't that inherently make an El Nino more destructive? Like if you have a hot weather event forming inside a pot of water that is already boiling, doesn't it supercharge it?
It is a very logical assumption, and it's what a lot of people expect. But climate model research actually suggests something really counterintuitive. A study by researcher Sion Tribetti suggests that future extreme super El Niños may actually lose their punch in a rapidly warming world.
Lose their atmospheric punch. How is that physically possible?
Because atmospheric convection, the violent shifting of winds, and the rising of storm clouds, is driven by temperature gradients. It is driven by the difference in temperature between the hot El Niño waters and the cooler waters surrounding it.
So if the background ocean is already relentlessly hot everywhere, that relative temperature difference shrinks.
Exactly. If everything is hot, the atmosphere doesn't react as violently to the El Niño pool because the contrast is gone.
Oh, wow. It's like if I'm in a freezing cold cabin in the winter and I turn on a space heater, the contrast is massive.
Right.
The hot air rises violently, the cold air rushes in to replace it, and you get this intense circulation of air in the room. But if I take that exact same space heater and turn it on inside a 180-degree sauna, nothing really happens. The temperature gradient isn't steep enough to drive the convection.
That is a perfect thermodynamic analogy. The El Niño is the space heater, and the global ocean is becoming the sauna. Because the contrast is weakened, the atmospheric reaction, the shifting jet streams, and altered rainfall might become less distinct from an ordinary year in some regions.
But just because the atmospheric punch might be slightly dampened, that definitely does not mean the oceans aren't suffering. The local and global fallout from this baseline heat is staggering. The sources include reports showing that ocean warming globally above 1.5 degrees Celsius has triggered persistent year-round marine heat waves.
And we really need to define what a marine heat wave actually does, because it is far more insidious than just warm water. When the water temperature stays abnormally high for months or even years, it fundamentally alters the physics of the water column. It creates relentless nutrient stress.
Because the hot water acts like a lid.
Precisely. It creates intense thermal stratification. Phytoplankton, which form the absolute base of the entire marine food web, they live at the sunlit surface. But to survive, they need cold, nutrient-rich water to well up from the deep ocean to feed them.
Okay, I see where this is going.
Yeah. When the surface layer gets extremely hot, it becomes buoyant and rigid. It creates a physical barrier, stopping that cold water from upwelling. The phytoplankton starve, the small fish starve, and the entire ecosystem just collapses. NASA satellites are actively detecting major ocean nutrient stress across vast swaths of the globe right now.
And we see the consequences of this localized chemistry shifting too. There's 2 decades of data in the reports showing the Biscayne Bay in South Florida has become warmer, saltier, and significantly more acidic. The entire chemical character of the coastal ecosystem is transforming.
It's a complete shift.
And we also know that our traditional conservation methods, like drawing lines on a map, aren't enough to stop this. There was a preprint shared by David Schiffman finding that only a tiny fraction of threatened sharks and rays have even minimal habitat coverage inside marine protected areas. You can't put a fence around a marine heat wave.
Which is exactly why we are starting to see mainstream scientific discussions of truly drastic measures. Our sources include a highly controversial study looking at solar geoengineering.
Okay, this is the stuff that sounds like a sci-fi movie where everything goes horribly wrong. We are talking about stratospheric aerosol injection, right?
Yes. The research suggests that we could theoretically fly fleets of specialized high-altitude aircraft into the stratosphere and actively spray reflective sulfur dioxide particles.
Just spray it up there.
Yeah. By artificially mimicking the cooling effect of a massive volcanic eruption, creating that particulate mirror we discussed earlier, the study calculates we could shield up to 75% of the world's oceans from warming, preventing mass coral bleaching and nutrient collapse.
The physics might work, but the side effects could be apocalyptic. I mean, who gets to decide the thermostat of the planet? What if spraying sulfur into the stratosphere alters the monsoon rains over India that billions of people rely on for agriculture?
It is a terrifying Pandora's box of geopolitical and ecological risk, but the fact that it is being seriously modeled and debated in top journals shows you just how desperate the situation in the oceans has actually become.
And that desperation isn't limited to the liquid water. The combination of this baseline warming and extreme weather is having immediate devastating effects on the planet's frozen reserves and the hidden ecosystems they support. Let's look at the vanishing cryosphere.
The reports coming out of Europe regarding their ice are incredibly grim. Swiss glaciers, which are iconic landscapes and absolutely vital for freshwater supplies across Central Europe, have completely exhausted their protective snow reserves. And the reports emphasize this happened by late June.
Now, when I was reading this, I had to stop and think about the physical structure of a glacier. So a glacier isn't just one solid block of ice. It relies on a fresh coat of snow every winter to survive the summer, right?
Yes, the protective snow reserve is all about the albedo effect, reflectivity.
Right.
During the winter, the glacier gets covered in a thick layer of fresh, bright white snow. That fresh snow has a very high albedo. When the summer sun hits it, it bounces the solar radiation back into the atmosphere, keeping the ancient, compressed glacial ice underneath perfectly cool and insulated.
But because of the extreme heat domes we discussed earlier, that fresh white snow melted away incredibly early in the season.
Exactly. And once that fresh snow is gone, the dark, older, dirtier glacial ice is exposed directly to the relentless summer sun. Because it is darker, it absorbs the heat instead of reflecting it. The ice warms up, melts faster, and exposes even more dark ice. It drastically increases the risk of severe summer melt. It is a devastating, accelerating feedback loop.
And it's not just the ice that we lose. There is a fascinating, albeit depressing, article in the stack highlighting that when these glaciers vanish, the hidden life they support vanishes too. We aren't just talking about polar bears losing sea ice. We are talking about micro-endemic species.
Right.
Tiny organisms, specific microbes, ice worms, unique insects that have adapted over thousands of years to thrive in the exact temperature and chemistry of frigid glacial meltwater. When the glacier disappears, that specific river dries up or warms up, and those specialist organisms face absolute local extinction.
This ties into a much broader, deeply concerning biological trend. We have a massive study in our sources from the University of Arizona comparing more than 5,100 plant and animal species globally.
That's a huge study.
It is. And they found that climate-driven local extinctions are now especially severe in temperate regions. It is a phenomenon scientists call ecological network rewiring, which was heavily highlighted in a recent issue of Nature Review's Biodiversity.
Ecological network rewiring, I mean, it sounds very clinical, but what does it actually mean for the animals and plants on the ground?
It means the fundamental rules of survival, the rhythms of nature, are changing overnight. Life is frantically scrambling to adapt. Species are being forced to migrate up mountains to find cooler air, or they're shifting their biological schedules, or fortunately, they're just dying out.
Yeah.
The intricate, synchronized connections between a predator and its prey, or a specific flower and its pollinator, are snapping and reforming in chaotic, totally unpredictable ways.
The sources gave some fascinating examples of this rewiring happening in real time. For instance, phenology, the timing of biological events. Researchers found that Gen 2 penguins in Antarctica are coping with marine heat waves by breeding earlier in the season. Yeah, they are literally shifting their biological calendars to try and ensure their chicks have access to food before the heat disrupts the local fish populations.
And on the flip side of that, we are seeing climate change spurring unexpected physical changes, like weight gain in owl monkeys in the Amazon and Chaco regions.
Wait, how does the climate make a monkey gain weight?
It basically comes down to the disruption of the fruiting cycles of the trees they rely on. As the temperature and rainfall patterns shift, the trees might produce an overabundance of certain fruits at strange times, or the periods of food scarcity might shift, altering the monkey's metabolic needs and foraging behaviors. It's a ripple effect through the entire food web. And speaking of Antarctica, while the penguins are shifting their breeding, human scientists are struggling to keep up. The worsening extreme weather in Antarctica is making physical fieldwork significantly harder, forcing conservationists to rely really heavily on remote sensors and new technologies to collect data.
But the science is trying to give us a fighting chance to anticipate these shifts. There's a new ecological warning system mentioned in the reports that can forecast wildlife heat risks up to 9 months ahead.
That's incredible.
It is. Using advanced atmospheric prediction tools, Conservationists might actually know where a deadly heat wave will strike an endangered population almost a year in advance, allowing them to potentially intervene.
That is a massive breakthrough for triage conservation. But if we connect this to the bigger picture, this ecological rewiring isn't just happening to penguins in the ice or monkeys in the jungle. The exact same disruption is happening to the domesticated ecosystems we rely on.
Right.
It is directly impacting the crops that sustain human civilization. The future of land, soil, and human food security is absolutely on the line here.
This brings us to the nutritional crisis, and this is something I think very few people are talking about or even realize is happening. We all know that droughts can kill crops, right? A
Right.
lack of rain means no wheat. But there is a silent, insidious crisis happening with the crops that do survive the heat. Climate stress, and specifically the massively elevated levels of CO2 in the atmosphere, actually reduces the micronutrient density in staple crops.
It is often referred to in botany as the junk food effect.
The junk food effect.
Yeah, it comes down to plant physiology, specifically in C3 plants like wheat and rice. When you pump vastly more carbon dioxide into the atmosphere, the plants use it to perform photosynthesis faster. They essentially gorge on the carbon, they grow larger, and they grow much faster.
Which, sounds like a good thing. More plant, more food.
It sounds good until you look at the chemistry. While they are rapidly synthesizing all these extra carbohydrates from the air, they are not simultaneously drawing up more iron, zinc, or nitrogen from the soil to match that rapid growth.
Oh.
The vital minerals are being diluted by the sheer volume of sugar and starch the plant is creating. They are literally bulking up on empty calories.
So a bowl of rice or a loaf of bread baked in 2026 literally contains fewer vital micronutrients, less protein, less iron, than the exact same serving size did 50 years ago.
Exactly. So even if our agricultural systems manage to grow enough raw tonnage of food to feed the population, millions of people could still suffer from massive hidden malnutrition because the food itself has been chemically hollowed out by the atmosphere.
And the proposed solution in our sources is wild. Because we can't quickly pull the CO2 out of the air, scientists are turning to CRISPR-Cas9 and other advanced genetic technologies to fundamentally alter the crops.
Right.
The Biochemical Society is working extensively on engineering resilient protein sources, specifically tweaking the genetic pathways of legumes like chickpeas to make them tougher and actively more nutritious despite the CO2.
It is a brilliant, highly targeted application of technology, using CRISPR to edit the specific genetic pathways of a plant so that its root system actively absorbs more zinc, or so that it maintains its protein synthesis pathways even under heat stress, is a staggeringly powerful tool for human adaptation.
I see the utility, I really do. But I have to push back on the philosophy here. Are we just genetically engineering our way out of a problem we caused instead of fixing the root cause? It feels like we're treating a gaping gunshot wound with a really advanced genetically engineered Band-Aid instead of just taking the gun away.
This raises one of the most fundamental debates in climate science today: mitigation versus adaptation. Mitigation is stopping the carbon emissions, taking the gun away.
Right.
Adaptation is dealing with the reality of the climate we've already locked in, deploying the advanced Band-Aid. The harsh, pragmatic reality of 2026 is that we have no choice but to do both. The surplus heat is already in the ocean. The CO2 is already in the air.
Yeah, we can't ignore that.
We cannot mitigate fast enough to save the global food supply from the stress that is already baked in. We must rapidly adapt the biology of our crops to survive the next 30 years, while simultaneously fighting tooth and nail to lower emissions for the next century.
And there is genuine good news on the agricultural front. It's not all doom and gloom. A massive study from the University of Illinois Urbana-Champaign found that global rice production actually nearly doubled over the past 50 years, despite the mounting climate stress.
That's huge.
And that was largely due to smart agronomy, better management, and the Green Revolution breakthroughs.
Which proves that human ingenuity and scientific management can outpace climate stress, at least for a time. And we're still making incredible fundamental discoveries about the soil itself. For instance, researchers just uncovered a massive hidden phosphorus reservoir in the dirt, specifically DNA-bound phosphorus.
Okay, stop right there. I know phosphorus is one of the 3 main ingredients in agricultural fertilizer, along with nitrogen and potassium. We literally mine it out of rocks. But what does it mean for phosphorus to be DNA-bound in the soil?
Well, soil is not just dead dirt, right? It is a thriving, microscopic ecosystem. When microbes, fungi, and plant roots die, their cellular material decomposes, A massive amount of natural phosphorus gets locked up inside the residual DNA strands of that dead organic matter.
Interesting.
Historically, it was incredibly difficult to measure or extract this specific pool of phosphorus. But researchers have developed a new, simpler chemical assay to measure it, which is vital for sustainable agricultural management.
Why is measuring it so important?
Because if farmers know exactly how much natural phosphorus is locked in the microbial debris of their fields, they can use specific cover crops or bacteria to unlock it, rather than continually relying on mined chemical fertilizers.
Oh, that makes sense. It's about understanding the microscopic mechanics of the soil so we can actually work with it rather than just dumping chemicals on top of it. And here's a finding from nature that completely threw me for a loop.
Hmm.
We always assume that a hotter earth means degraded, dried out, dead soil.
Sure, that's the assumption.
But a study by Pablo Garcia Palacios found that warming actually enhances soil carbon accumulation in some specific contexts. Wait, warming helps the soil store more carbon.
It is incredibly counterintuitive, but it speaks to the immense complexity of the carbon cycle. In certain ecosystems, warming accelerates the biological processes. The plants grow faster, and their root systems grow and die faster. It's a process called root turnover.
Okay.
This rapid root turnover pumps carbon deep into the soil faster than the soil microbes can decompose it and breathe it back out as CO2. So the net effect in these specific contexts is actually more carbon being driven into the ground.
Wow. Furthermore, there's another study showing that plants are boosting their carbon uptake through water efficiency. As the world warms and the air gets drier, plants get incredibly stingy with their water. They close their stomata, the little pores on their leaves, to prevent water loss, which unexpectedly alters how their canopies expand and how efficiently they sequester carbon.
Nature is dynamic. It is actively fighting back and attempting to find a new equilibrium. And scientists are trying to decode these complex feedbacks in some really creative ways. We have researchers at Penn State who are using lab-created artificial permafrost to study how the thawing Arctic ground behaves.
I read that and couldn't quite picture it. They literally built fake permafrost in a lab, like in a giant freezer.
Essentially, yes. They construct complex, multi-layered soil profiles, they call them cryosols, matching the exact physical and chemical composition of Arctic peat and mineral soils. Then they freeze it in massive, highly controlled environmental chambers.
Ah, so clever.
By slowly raising the temperature, they can use laser spectrometers to measure exactly how the microbial communities wake up, and precisely how much methane and CO2 off-gases as the ice melts. They can isolate the variables in a way that is impossible to do while shivering in a tent during extreme weather in the actual Arctic.
It's brilliant. They bring the Arctic to the lab to decode the exact timeline of the methane time bomb. But this brings us to a really harsh reality about all these scientific breakthroughs. You can engineer the perfect CRISPR crop or design the perfect wetland restoration strategy based on soil microbes. But it means absolutely nothing if the humans on the ground refuse to implement it.
Right.
Which brings us to the fascinating research from Aarhus University on the landowner dilemma.
Yes. We know scientifically that restoring low-lying, degraded agricultural soils back into natural wetlands is a massive win for the climate. Wetlands trap huge amounts of carbon and restore biodiversity. So the logical policy response is for governments to simply pay landowners to flood their fields.
Makes sense.
But the Aarhus researchers found that climate compensation, just throwing money at farmers, isn't always enough to convince them to do it.
Now, rationally, if the government offers to pay a farmer more money than the crop on that bad soil is worth, shouldn't they just take the check and flood the field?
From a purely economic standpoint, yes. But farming isn't just a spreadsheet, it's an identity. For generations, these families have seen their primary role in society as producers of food, as the tamers and stewards of the land. Asking them to deliberately flood their fields, to let the land go wild and swampy, feels to some like a profound admission of defeat or a rejection of their generational heritage.
It's an attack on their identity. The research emphasizes that transitioning land use isn't just an economic transaction. It requires building trust, respecting local identity, and deeply understanding the cultural context of the rural communities you are asking to change.
Which is the perfect bridge to our next major topic. Because top-down edicts, whether they are about agriculture or energy, clearly have their limits. Ultimately, surviving the climate crisis requires human coordination, nuanced policy, and truly inclusive action. Let's look at the human element.
Absolutely. The transition to a sustainable future must be inclusive. And right now, the data shows that it often isn't. There is a powerful article in the conversation that highlighted 3 urgent ways climate action must be made more inclusive for the 1.3 billion disabled people globally.
1.3 billion people. That is a staggering demographic, roughly 16% of the global population, that is routinely, systematically left out of disaster planning and climate adaptation.
Entirely left out. The article emphasizes the desperate need for accessible urban planning. Like when a city designs a cooling center for a heat wave, is it wheelchair accessible? They call for inclusive early warning systems for extreme weather. Are the flood warnings accessible to the deaf and blind communities?
These are basic necessities.
And most importantly, they demand the active participation of disabled individuals in the actual climate policy decisions. If a city's emergency evacuation plan relies on buses that don't have wheelchair lifts, that policy hasn't just failed, it is actively discriminatory.
It is a matter of life and death. And similarly, another critical piece from the conversation explains how extreme heat is severely harming remote First Nations communities. The authors make an urgent, incredibly powerful argument that climate adaptation cannot just be dictated by scientists in a sterile lab. It must listen to local indigenous knowledge and lived experience.
Because these communities have managed these specific local landscapes for millennia. They know the rhythms of the land, the behavior of the local fire regimes, better than any satellite model.
Exactly. Think about cultural burning versus hazard reduction burning. Indigenous fire management is a highly sophisticated, deeply nuanced practice that reduces fuel loads while actually protecting the ecosystem.
Right.
When modern bureaucracies ignore that knowledge, we get catastrophic megafires. It is a phenomenal tragedy when we ignore the practical realities of the people who actually live on the land.
But unfortunately, ignoring the practical realities seems to be a recurring theme in the broader climate policy landscape. Look at the 5th National Climate Assessment mentioned in our sources. It highlights the severe impacts hitting the U.S., but also emphatically states that we currently have all the technological and economic tools we need to cut emissions and adapt.
The tools exist.
Yet, as another report warns, fragmented environmental policies risk incredibly costly failures.
We constantly see climate policies and nature policies working at cross purposes, wasting billions of dollars, and sometimes even harming the ecosystems they're trying to save.
I saw a perfect example of that fragmentation in the sources regarding a coastal carbon removal technique. It involves adding alkalinity to seawater to help the ocean absorb more carbon base, basically dropping crushed antacids into the bay.
Right.
It sounds great on paper, but if it is pushed too far without considering the local biology, it can trigger secondary chemical reactions that cause the ocean to off-gas CO2, undermining the whole effort. It's well-intentioned, but it is policy operating in a silo.
And it turns out the scientific community itself might bear some of the blame for this massive policy disconnect. An extensive analysis out of the University of Cambridge looked at hundreds of climate mitigation papers. They found that the policy recommendations included in these scientific studies are often treated as an absolute afterthought.
Meaning, the scientists do the hard math, prove the climate is warming, but then provide zero practical advice on what a mayor or a senator should actually do about it.
Precisely. The policy suggestions are frequently missing entirely, hopelessly vague, or totally disconnected from the actual results of the study. It severely weakens the science-to-policy pipeline.
Wow.
If scientists don't do the hard work of translating their complex data into actionable, specific, legally viable policy steps, politicians are left to guess. And guessing leads to fragmented, failing policies.
Now, speaking of the fraught gap between science, policy, and politics,
Right.
we are looking at a stack of sources that touch on the political and informational landscape. And before we dive into this next specific batch of reporting, let's set some ground rules for ourselves. This next section touches on some highly politically charged territory.
Yes. Our goal today isn't to take a side, endorse a politician, or condemn an industry. We are strictly here to act as your tour guides through the information landscape.
Right.
We are impartially reviewing the source text provided to us, mapping out what is being reported, and how the flow of information itself is becoming a critical climate variable.
Exactly. Our job is just to show you the landscape of information as it was reported in this stack. So in our sources, there's a piece of investigative journalism from ProPublica, which was shared and highlighted by climate scientist Michael E. Mann. The investigation looked into a specific educational event connected to fossil fuel interests.
Right.
According to the ProPublica report, this event was focused on teaching sitting judges a, quote, healthy skepticism of climate science.
Additionally, our sources include another post where Michael Mann pointed to an article published by the Bulletin of the Atomic Scientists. This article discussed a specific climate disinformation narrative that, according to the publication, was recently platformed by Donald Trump.
Again, we are simply reporting the existence of these articles to illustrate the deeply complex, highly contested, and often contradictory information landscape in which climate science currently operates. Whether it's happening in the courtroom, where judges are being educated on science, or on the political stage, where narratives are amplified to millions of voters, the hard data we've discussed today about oceans, glaciers, and atmospheric physics is constantly colliding with human narratives, economic interests, and political platforms.
It serves as a stark, necessary reminder that scientific facts do not exist in a vacuum. The dissemination of information, how it is framed, who pays to frame it, and who is consuming it is arguably just as critical to the future trajectory of the climate as the carbon molecules themselves. The narrative shapes the policy, and the policy shapes the atmosphere.
Okay, let's take a deep breath. We have covered a massive amount of ground today. From the terrifying invisible physics of Earth's doubling energy imbalance to the localized toxic ash raining down on Los Angeles. From the thermodynamics of the new El Niño index to CRISPR-edited chickpeas and the absolute desperate need for disabled inclusion in our climate policies. I want to bring it all back from the global and the political down to you, the listener. And honestly, amidst all the murky diagnostics, I want to highlight a few final genuine reasons for hope.
Because the news is not all bad, and it is crucial to remember that. The journal Nature recently published a fantastic roundup of inspiring science stories, reminding us of incredible species recovery efforts and massive accelerating global progress in the rollout of renewable energy.
Yeah.
We are seeing advanced maps being developed that show exactly where European landscapes can be managed to advance both climate mitigation and biodiversity goals, simultaneously proving that smarter land use can unlock economic gains while actually healing the ecosystem.
We even saw a report in the stack that India gained 2.1 million hectares of dry woodland in a single decade. That is massive reforestation. And there are incredible technological leaps happening completely outside of biology, too. Like new methods being developed to convert wasted infrared light into useful energy, which could massively boost the efficiency of solar panels and even night vision tech.
And let's not forget the simplest, most elegant technological solution of all, which was wonderfully highlighted by Scientific American. A human on a bicycle remains among the most thermodynamically efficient forms of travel and movement in the entire world.
That's amazing.
It requires zero fossil fuels, it dramatically improves cardiovascular health, and it costs almost nothing to run.
I absolutely love that fact. Amidst debates about stratospheric solar geoengineering and building artificial lab permafrost, the humble bicycle is still a climate superhero. But as we wrap up this deep dive, I know we promised a final provocative thought for you, our listener, something for you to mull over as you go about your day.
Yes. If you want to know exactly where you stand in all of this, scientists at the University of Reading have created something fascinating called the Real Scoreline. It is a new, comprehensive scoreboard comparing nations based not just on the political promises they make, but on what they actually do.
Okay, what do they track?
It meticulously tracks current emissions, fossil fuel dependence, citizen heat stress exposure, future warming projections, and the actual legislative strength of their net zero commitments. It essentially calculates the objective climate penalty each nation is currently facing.
So I challenge you, the listener, to ponder this. If you looked up your own country, your own state, or your own region on the Real Scoreline, where do you honestly think you would rank? Are you living in a place facing a massive mounting climate penalty because of systemic inaction? Or are you in a region actively leading the charge toward adaptation? And more importantly, zooming all the way down to the micro level, what can you do in your own community, using your own specific skills to help change that score?
Because at the end of the day, as murky as the diagnostic waters are, and as broken as the planetary X-ray machine might seem, when we look at the immense, chaotic complexity of this Earth, the basic underlying truth remains incredibly clear. The patient is running a fever, we know exactly why, and the treatment plan isn't a mystery, it just requires the collective human will to administer it.
So keep asking the hard questions. Keep demanding clear answers from the muddy waters, and most importantly, keep learning. Until next time, thanks for joining us on this deep dive. Take care of yourselves and take care of each other.